and the amount of natural gas that would be stored in that fuel tank. However, if I fill the fuel tank with a MOF, in this case a MOF it's an aluminum MOF, we call MOF 519, you can see the uptake of methane. And if I go, let's say, to 60 or 80 bar, you can see that I can store in that fuel tank 2 times, perhaps 3 times the amount of natural gas when the MOF is in the fuel tank than when the MOF is not in the fuel tank. So that means that within a fuel tank that is filled with MOF, because it's a microporous material or nanoporous material, the methane molecules are compacted within the pores by virtue of their interaction to the internal surface of our material. And therefore, you can store more natural gas in the presence of MOF than without the MOF. And so that means an automobile that has a fuel tank filled with MOF and natural gas can travel 3 times the distance without having to refuel. And furthermore, this is an automobile that has been driven all over the world and driven to 100,000 cycles of fueling and fueling and recycling, and where our material does not leave the natural gas tank. It stays there for the lifetime of the car. Okay, and so this is a viable application for commercialization. Another application I want to discuss is water harvesting from air. If you have those pores, as I described before, and you can take natural gas in them, why not take water? So the key here is to design a material that sucks up water, as you see here, with this sharp isotherm. And that means that as soon as the material is exposed to this low pressure of water, which is in the atmosphere, it takes it up and gets saturated. And then you can remove it at a different temperature. So for example, we did this for Tabuk, the city north of Saudi Arabia. And in Tabuk, you can take this material, we call it MOF 841. During the night, the temperature is 25 degrees. It absorbs water from the atmosphere, fills the pores, and during the day, you can release that water at 45 degrees. And you can see here the cycle of uptake and release up to 80 cycles, and the maintenance of the performance is still maintained or still sustained. So our idea is to design a system that not just works between the day and night temperature shift, but that can work in every home at any time. So an ongoing uptake of water from air. And so this system would work on solar energy, and basically it would require you to push air through a bed of our material and then condense it and then deliver fresh water. So to give you an idea, for the material I just showed you, if I take a tank, which is not very much unlike a tank that is already in Saudi homes, 1 cubic meter capacity, right? That's most water tanks are about 1 cubic meter in capacity. I can deliver 100 liters of water every hour at a humidity not very much unlike the humidity you have here in Riyadh. Okay, so that's what we are working on. That is what is possible in the laboratory. And now we are developing a prototype to show that in fact this can work. And the key here, again, the key is that we've discovered a material that sucks up water from the atmosphere, okay, where water is in low concentration, using this sharp isotherm, okay, and that's what makes the material efficient and high performing. Another application we are working on is carbon dioxide capture. In a typical sedan automobile, you have 25 kilos of petroleum, And when you burn that, you've emitted 81 kilos of carbon dioxide. So you can imagine the scale of the carbon dioxide problem. The problem with carbon dioxide is not capturing it, it's capturing it in the presence of water. Because every capture material has to compete with water. Carbon dioxide competes with water. Water likes to stick on the interior of MOF and other porous material much strongly than carbon dioxide. So we need to develop a way to create a material that can operate or that can seek out carbon dioxide without the complication from water. And so here's a material where we functionalize the pores with methyl and with primary amine. The primary amine is going to take up the carbon dioxide. I'm showing the methyl just for comparison. You can see that without water, when I expose my material to carbon dioxide without water, the carbon dioxide is held into the pores until the pores are filled, then it breaks through. This is a breakthrough diagram. When I introduce water into this, you can see the efficiency of the material goes down. Okay, and that's what typically a porous material would do. However, if you functionalize your material with primary amine, you can see here, without water, it holds carbon dioxide very well. And as you introduce water, it still maintains the same efficiency as without water. And that's because these methylamines are specific to carbon dioxide binding. And in fact, they work better in the presence of water. Another way to do it is to create a hydrophobic MOF so that the water is prevented from getting through. So here's the same experiment, a breakthrough experiment, but now you have a dry feed of carbon dioxide and nitrogen, and you can see carbon dioxide being held into the pores. It comes out at 0, and then before it breaks through. And as I introduce water, exactly the same performance as the dry bed. And this tells you that the idea of capturing carbon dioxide in the presence of water is possible, and it is viable. And so this is a very, very exciting development in the field of carbon dioxide capture. Not only can we capture carbon dioxide, but we can also convert carbon dioxide to a fuel. In this experiment, we're converting carbon dioxide electrochemically to carbon monoxide, which is a very important starting point for many chemicals. Thank you. And in this case, we take a methylated porphyrin and do COF chemistry on it, meaning we link it up to make imine. So we make a framework, and the framework has the catalyst repeated throughout the framework. We make this framework and its expanded analog. And the performance of this catalyst is shown here. It is highly selective to the conversion of carbon dioxide to carbon monoxide in water. So we are operating in water, and these are the turnover numbers. We can achieve a turnover number of 296,000 and a Faradaic efficiency for carbon monoxide of 91%. This is the best catalyst for converting carbon dioxide to carbon monoxide. Why? Because we've taken the catalyst and hooked it up into a framework. And now the active site is repeated throughout the material, and it is accessible. It's also, by virtue of linking it up into a framework, you are hooking it up electronically into a framework. And so you can modify the active site nearly at will. So the next experiment is about carbon dioxide to methanol, another important chemical. For that, we use a zirconium MOF, not very much unlike the MOFs I have been discussing. Here we take a copper catalyst, which are these dark dots, inside nanocrystals of that MOF. Okay, so remember the MOF is porous, and so now I am exposing the copper crystals or the copper catalyst to an incoming substrate by that substrate diffusing through the MOF. And you can see here the MOF is crystalline, it's also porous. So that means that it is accessible. We also, for comparison, grow copper crystals on the surface of the MOF nanocrystals, just for comparison. So how do they perform? Well, the copper inside the MOF, impregnated into the MOF, does much better. These are the turnover number, the frequency, for methane production. So it does better than copper on MOF. But let's compare to the state-of-the-art catalyst, industrial catalyst. The industrial catalyst is a copper zinc oxide alumina catalyst, shown here in yellow. Our catalyst is in gray, and that's the copper, the copper in the MOF. And you can see that even at lower temperature, our catalyst does a lot better than the industrial catalyst. And the reason for that is that the copper is now accessible, a copper particle, a copper catalyst particle is now accessible from all sides. So it's very, very active, and it cannot sinter with other copper particles, as normally would be the case in this chemistry. So I've shown you two examples, including carbon capture, but also carbon conversion into high value products. Now I want to show you why I talk about framework chemistry as opposed to molecular chemistry. Framework chemistry, because the framework, I'm using the framework as a chemist would use a molecule, meaning I can transform the framework in the same precision that a molecular chemist would, or an organic chemist would transform their organic molecules. But I can do it on a framework, which contains Avogadro's number worth of molecules or building units. Okay, but I can do that without affecting the crystallinity or the porosity of the framework. It does not get destroyed. It only gets modified by the chemistry that I'm doing. So let me just give you an example. Here's a crystal of a MOF we call MOF 74. You don't have to worry too much about all these abbreviations. But this MOF, we install on it a Bach-protected primary amine. Okay, we start out with a methyl, we make this, and now I want to show you 7 reactions that are going to be run on the same material. Okay, Bach deprotection, microwave it at 230 to make the amino. And now we are adding an alanine unit into the pore. So that was reaction 2. This is reaction 3, reaction 4, reaction 5, reaction 6, and reaction 7 to produce a short peptide. So all those chemical reactions are being run on the framework to produce a short peptide into the pores. Now, all of this would be ordinary if it wasn't for the fact that your crystal maintains its crystallinity. So I'm using the macroscopic crystal as a molecule, and it maintains its porosity. And therefore, this is the birth, really, of framework chemistry. So why do we do this? We do this because if you can modify the pores in the precision that I just showed you, then perhaps we could do catalysis that is as selective as enzymes. So here's an enzyme called TEV protease, and this is the active site of the enzyme. This enzyme is designed to break only this red amide bond, not the blue ones. This is the only enzyme that is capable of this kind of reaction. No other biological material or man-made material could do this bond breakage as this enzyme would. So our question was, if we modify our MOF with the active site of this enzyme, meaning I build the active site of the enzyme chemically and covalently in the pores of this MOF, will I get the same kind of reaction? And the answer to that is yes, we can. And in fact, we just published this paper where we showed that this MOF, when modified with the essentials of the active site of the enzyme, does exactly what the enzyme does, and that is cleave that special amide bond. Okay? That means that for the first time, you're able to mimic an enzyme in a very special way, as I just showed you, with the same selectivity as the enzyme. Okay? So So I think that we are looking here at the emergence of chemistry beyond the molecule. Let me now turn into two other recent developments in my lab. One of these developments is how to crystallize molecules. Chemists, some of you in the audience, know very well that we spend almost 90% of our time trying to make crystals of our new molecules. But molecules don't want to crystallize. And the more complex they are, the worse the challenge is. And so molecules want to wiggle. Okay, they want to wiggle, and so they can't stand still so that we can do X-rays crystallography on them. So what we've done is that we accept the fact that they can wiggle, or they want to wiggle, but now we can cause them to pause. Okay, let me show you how. So here's a MOF. This MOF is MOF 520, one of the MOFs that we were examining for methane storage. Okay, you don't need to know what the structure necessarily is. It's in front of you, but it's a complex structure. It's a porous structure, but made from these aluminum wheels and that triangular organic unit. But there's something very special about that aluminum wheel. The aluminum wheel is made from 8 aluminum octahedra. And you see carboxylates that are on the periphery. These carboxylates are the ones that are coming from the organic linker that link these together to make the MOF. But there are also other carboxylates drawn in yellow. These are the carboxylates of formates. They are terminal carboxylates. They don't go anywhere. They just cap the aluminum sites. And so in the structure, when we were doing methane storage, we were testing this MOF for methane, and we were replacing the formate with benzoate or naphthawate, heptanoate, and then checking what effect does that have on methane storage. Well, it turns out that it didn't have much effect, but we noticed that for the heptanoate, we can get the crystal structure of the heptanoate. This is usually so mobile that it's almost impossible to get a crystal structure of in a material. So what we then realized that in fact, if you could replace the formate with any one of these functionalities, then no matter how complex your molecule is, you should be able to crystallize it, or you should be able to stop it from wiggling in the pore. Because now you have functionalities on these complex molecules, shown here in red, blue, and green, where they would replace the formate and then bind to the aluminum. So that we anchor them onto the aluminum, and then the rest of the molecule forms weak interactions with the framework, and therefore now it's stationary, and now you can get a crystal structure of it. So just to elaborate what I'm saying, here's a molecule where it's bound covalently to the framework in yellow. That's the framework. And you can see weak interactions of this molecule with the framework. Okay, so you can get crystal structures of hormones that nobody knew the structure of before that. So these are plant hormones, and the structures are so accurate that you can determine the double bond from the single bond, even at 30% occupancy. So if I ask an organic chemist, could you crystallize this molecule? They will say not with great ease. Now you can just impregnate that into a MOF and get a crystal structure of it that way. This is another, jasmonic acid is a very well-known plant hormone, and there was only NMR evidence for it, but no crystal structures. Now, using MOFs, we can get the crystal structure of this material. So we think that this technique of getting crystal structures of complex molecules is widely applicable, not just to plant hormones, but to a lot of metabolites and small molecules, and including proteins, crystal structures, simply by coordinatively aligning them, as the title of our paper, Coordinative Alignment of Molecules in Chiral Metal Organic Frameworks. The last topic I want to cover is weaving. So weaving is the oldest method of making fabric, and it's still being used today. And there is a reason for that. It's a way to make flexible fabric, flexible material, and resilient material, right? I can flex it, I can bend it, and still maintain its function. So, and we can add that to frameworks. If you could make frameworks not just rigid, but also flexible without losing their structure, then we can apply dynamics into frameworks. But how do you do it? Okay, you would have to take a chain of molecules that are covalently linked and interlace them in and out of each other in the way you see here. And that chemists cannot do, because there's no way you're going to take a chain like a polymer, throw those polymers together and have them come together in this intricate way, the same way throughout the material. So if you ask any chemist, could you do this? They will tell you no. Okay? You might be able to entangle them, but you will not be able to do this in a homogeneous way. Now, from my point of view as let's say a reticular chemist, a chemist that thinks in terms of building blocks, all I need is a unit that interlaces like this, an up and down unit, let's call it. Once I have that, then I can link it up using MOF or COF chemistry to make the weaving. Okay, so I don't actually weave, but what I get is a woven structure by linking the intersections. So it's a lot easier than weaving, but the result is the same as weaving. And your threads could be straight threads or they could be helical threads. So the way we do this is by using this building unit here. This building unit, let's see if I can find my cursor here. This building unit is made from two molecules shown. They're the same molecules, except I'm showing them in two different colors, yellow and blue, because the yellow is going to be one fiber and the blue is going to be another fiber interlacing with it. They come together by virtue of the phenanthroline to make, with copper 1, to make a complex. We functionalized, by the way, this year's Nobel Prize was for this molecule, but where they have closed, excuse me, let me find the cursor again, where this was closed with a polyether and that was closed with a polyether. And that made what's called a catenane, the mechanical bond. So we're using the same kind of technique, except in our case, we functionalize the edges with aldehyde, and now we copolymerize them with amines to make an imine fiber. You can see the imine fiber in blue and the other imine fiber in orange to make an extended structure. Okay? Now, the nice thing is that I could then add KCN and remove the copper. When I remove the copper, I have a weaving structure or a woven structure. And it is crystalline. So this is the analysis using electron microscopy and X-ray diffraction. You can see highly crystalline material. So we have figured out how to use the mechanical bond to weave chemical structures for the first time in the history of humanity. And that is shown right here in front of you. And so the powerful thing about this is now your threads are entangled and they can move with respect to each other without destroying the overall structure, just like any fabric would. And not only can we do that, but almost every structure you know, every network you know, could be woven. Okay, here's a structure that is well known to magnetic chemists or people who are interested in magnetism called the Kagome lattice. The Kagome lattice you can see here can be weaved. This silicate can be weaved. Quartz can be weaved. Primitive cubic can be weaved. Sodalite can be weaved. So almost any kind of extended structure could be made not just as a rigid framework as I showed you before for gas storage and catalysis, but also now you can incorporate this flexibility to have dynamics added. But also you could do braids. So the moment you figure out, as we did, how to do this up and down, now the possibilities are limitless. So finally, what I want to say is that we've developed control of the strong bond. We can make frameworks by linking building units through strong bonds, and therefore we've developed a whole new world of chemistry based on the framework. So I want to conclude with the following paper published in 1916. It was published by Gilbert N. Lewis. He was a professor at the university where I am, in the chemistry department at UC Berkeley. And he published this paper in 1916. It is now a landmark paper because his ideas in that paper, where he was linking atoms together to make molecules, are now form the basis of the covalent bond. He titled his work The Atom and the Molecule. And you can imagine the power of that covalent bond and what it has given us. It has not just given us his idea. This is Lewis. By the way, this is Gilbert Lewis of the Lewis dot structures that we learned as children in chemistry. That's the Lewis. And his ideas have led us to make polymers, to make entangled frameworks or supramolecular chemistry, vitamin B12. This is total synthesis, total organic synthesis. It has led us to make also these catenanes, but let me suggest that in fact what I have shown you today is an extension of the covalent bond by taking these molecules, both the covalently linked molecules and also the mechanically linked molecules, to make extended covalent frameworks. And so therefore, I'd like to say that I think we have now written the contribution, the atom, the molecule, the framework. So finally, I want to acknowledge my group members and also the funding and our collaborating partners both at CAXT and KFUPM and Aramco. And I want to thank you for your attention.
Thank you very much, Professor Omar. Thank you very much for your attention. Now it's time for a question. So you just have 20 questions to be spread between male and female. So 10 here and 10 there. So let's start with okay, go ahead, Professor. الميكروفون يا اوكي الميكروفون هنا الله يحفظ سوري Okay, go ahead, Professor.
Okay, thank you very much. Okay, thank you, Prof. Yaghi, for this very nice and informative lecture. My question is, you showed us some chemistry about the condensation of water from humidity. And we have seen in the market
Hello.
Something close to this. Are they using your same recipe, or are they using some maybe simpler just technology? Do you know anything about this?
Let me just say, we're not condensing water into the pores. We're actually taking water molecules from the atmosphere as gas and bringing them to the pores. They aggregate in the pores as vapor. And then as you condense them, they come out as liquid. what you see in the market that says, you know, water from thin air, all that stuff, sure, that's just dehumidification. But that's the energy dehumidification uses, like you dehumidify your home. You have to plug it into the wall. Okay, that's a lot of energy. That's a lot of energy because the water molecules are bound very, very strongly to the material, chemically. So now you have to heat up the water to take it out. So in our system uses minimal energy requirements. That's why I think it is much, much more viable as a material to deploy for this application. Yeah.
One more a question from the female section. Yes.
عندك أسئلة دكتور؟
دكتورة في أي سؤال؟ أوكي بروفيسور سيفا.
Thank you for an exciting lecture that you're making about hiding active sites inside a MOF, right, or AOA. Now, it's amazing that it works. If you put it on the surface instead of MOF, does it make a difference?
Well, I mean, the thing is, the surface is not as well defined as a MOF, right? You mean the MOF surface?
Yeah, so I'm wondering what is this so unique? I mean, for example, the secondary and tertiary structural changes in an enzyme does contribute to a reaction, to leading to the cleavage of what.
That is not yes. So what about the secondary and tertiary structure of the enzyme? How does it, you know, where is that in the MOF?
Got it.
Now remember, the enzyme is made from these amino acid chains that prop the active site into place. So I think what's going on in the MOF is that, okay, we propped, using the MOF backbone, propped the active site into position with the right chemical functionality and the distance between those chemical functionalities to have the same kind of selectivity. So it makes me think that the MOF is really a nice flexible backbone. We should not think about the MOF as a very rigid framework, although it is architecturally robust. But there's a lot, it's made of molecules, and molecules wiggle. So there's a lot of give in the backbone.
Thank you, Dr. Omar, for this new chemistry actually we learned. I got two questions. The first one, to extend the application for this material for energy storage, it has to be conducting. So what about conductivity for this MOF material? And how is the hydrogen storage? That's because it's showing methane storage. Can be hydrogen stored, and how much can be loaded over there?
Okay, thank you. Not all energy applications require that the material be conductive. I mean, I just showed you methane storage, you don't need conductivity. Hydrogen storage, we can store in MOFs. I didn't show it, but we can store at 77 Kelvin, we can store 12 weight% hydrogen, which is very interesting for stationary applications of MOFs, but not automobile applications. For automobile application, you need room temperature storage. Right now with MOFs, we can get 1 or 2% maximum, 2 weight% maximum. And so we need to increase the binding energy, which is right now stands at about 13 kilojoules per mole to about 20 kilojoules per mole before we get appreciable amount of hydrogen at room temperature. So the hydrogen storage is still a challenge and still moving forward with that. I showed you carbon dioxide conversion to carbon monoxide, carbon dioxide conversion to methanol, and there you need some conductivity. The coughs are slightly conductive. They're not conductive in the same sense as metals. But in the applications I just showed you today, you don't need much conductivity. Now, there is a lot of work now in MOF and COF chemistry where people are making highly conductive MOF materials, but and COFs. But I don't know if people are studying their reactivity yet. Yeah.
Thank you, Dr. Amar, for being with us and for the nice talk. My question actually is probably a fundamental question regarding the name of MAF. I personally had a controversial story with one of the reviewers. We were working on TCNQ, tetracyanokinodimethane, and that compound forms probably what they call charge transfer complexes. And at the same time, Kim Dunbar at Texas A&M consider those compounds as MOFs. So we just use that terminology that what we are making for thallium TCNQ is a MOF. Then we submit this to inorganic chemistry. Two reviewers, they said publish, and the other one, they said no. The reason why, because he said that thallium TCNQ is just salt and not metal organic framework. And he said if we're saying that, then we can consider any organic molecule with metal ion like lead acetate, for example, we can make this as a MOF. So we couldn't convince him that this is MOF. So how can we define MOF? Is it based on the network of the molecules itself, or it has to be non-ionic? Or so if you can outline that. Thank you.
Okay, thank you. When I first named these materials MOFs, I looked at them from the point of view of that they contain a metal, they contain an organic, and they are frameworks because they are linked together through strong bonds. So my definition is that they are porous, metal organic frameworks in which the building units are connected through strong bonds. There was an IUPAC meeting where people got together and they decided that a MOF, a coordination polymer is not a MOF. A coordination polymer is a metal organic. I hate this word polymer because they're really not polymers. They are crystals, they're extended structures. So that's a misnomer. But anyway, it's there. Coordination polymers. I would say that to be on the safe side and to obey the IUPAC definition, MOF is a metal organic framework in which the building units are linked through covalent interactions, but also that it has porosity. Just a comment about referees. You don't have to do what the referees want. If the referee is stupid, you don't have to do what the referee wants. Seriously. If you believe that what you have is what it is, and you have evidence for it, and you have precedent for it, then why have to follow some stupid referee comment? Most of the time, referee comments are very, very helpful, and they make the paper better. I'm an editor for a journal, and I know that almost 90% of the time, referee comments are very, very helpful in improving a paper. They improve my papers, they improve everybody's paper. It's a great way for us to work in academia. But there are some stupid referees, and I think you should just not listen to them.
Any question from the female section? Hello? Okay, the good news is that today we celebrate the 100 years of the starting of MAFs, I guess, right? It's like 1960.
Something like that.
Okay, that's good. So that's why we put...
It's not the start of MOFs. It's the start of the atom, the molecule, and we're relating the framework to that concept.
Okay. All right. Thank you very much, Professor.
Okay, thank you.
Thank you very much for your attention.
Nice talk, not very nice. They probably يستغربوا why you sat here. أقول لهم عشان ما بسمعش كويس.
How is this working? كيف الحين يشبك وين الاي تي هنا؟ في دكتور ما فلاشة؟ لا ما معك فلاشة؟
نعم.
فلاش
نعم.
موجود؟ maybe واحنا نستخدم ده؟ لا نحتاج بس هو مش
نعم معمول فيه.
المفروض اوتوماتيك بيعمل عرض كده حاجه يعمل فيو عرض
سامبل سامس دي على سامس لكن تقدر من هنا على طول.
بس عايزين الفن بتاع الصوت عشان يظبط العبد مش لاقي. طب لو شوفونا بس الاول.
شكرا.
طيب خلاص اتظبط. just
Okay.
Dear, sorry for this technical problem. Now with the second keynote speaker, Professor Mustafa Sayed, a native-born Egyptian. He received his bachelor degree at Ain Shams University in 19 something in Cairo. Then he got his PhD degree from Florida State University in 19 something. We don't want to mention that date exactly. I don't know. After doing his postdoctoral work at Yale and Harvard and Caltech, he joined the faculty of University of UCLA. He been like chair for Julius Brown chair and adjunct professor at Georgia Tech. So welcome, Professor Mustafa.
Thank you. Bismillah ar-Rahman ar-Rahim. You know, cancer is a very, very, well, it and heart attack are the ones that kill half the people in the world. How many of you know somebody, relative or a friend or that has cancer? Would you raise your hand, please? Could you raise your hand if you know somebody that has cancer? Very good. Yeah, it's a very bad disease indeed, and we up till now, they have not found a medicine for it to really cure it. Everybody gets it. Almost 85% of those that get it, they die of it. So it's one of the biggest enemy probably of human people that we have. Yeah. Now when that a new science came in, you always have to try the new science. Does it help? Does it help? So what I want to let you know today is some of the results of using gold nanoparticles in the shape of it's a nanorod, shape of a rod, that if you take a solution of it, inject it in the cancer lump, and let the solution goes around and around, the gold nanoparticle mixes everywhere, and then you expose light, near infrared light. اتفضل حضرتك اقعد استريح هنا. Near infrared light, يعني much weaker than this. This is too strong. And for a few minutes, and then leave it. Within 2 weeks, the lump disappears. What happened is the gold nanorod absorbed the near infrared light and heats up, make the whole region where the cancer is hot. And the heat, it doesn't have to be very hot temperature, 45 degrees centigrade. That melts the cancer cells and they get rid of the cancer. So of course that was a nice, nice result, of course. And so we followed this direction, and I'll show you some of the results that we have obtained. Excuse me, my goodness. I'll give you some of the, a little bit of nanotechnology. A lot of you know this. And the nano, then we'll get to the nanorod after that and give you the results of what we have seen all along in the last few years now. These are different nanoparticles that a lot of you familiar with, and gold and silver turn out to be very useful because of these optical and photothermal properties, but different kinds of nanoparticles have different properties, and they are used in different directions, of course. Okay. If you want to get to bind the gold nanorod to cancer cell, well, a cell has a certain functional groups on the surface. Cancer cell especially has a specific different ones, and all what you have to do is to bind the gold nanorod. In one end, you hook it to this peptide, and on the other end, that has the functional group that binds to the functional group on the cancer cells. And you just mix them together, and all the gold nanorods will just bind to the surface of the cell that the cancer cell that you want. In most cases, actually, we don't even need to do that. We just mix them together, and we heat the heat solution as a whole. We don't have to be very close to the cancer cell to heat it. We just heat the solution around the cancer cell. But this is just a way, if in the beginning when we didn't know if we want to make sure it binds to the cancer cell and so on, you can do these things, yeah. So the gold nanorods have two properties, very important properties when the light hits them. Depends on the size of the nanoparticle. If it is large, it scatters the light effectively. It gives you light back 10 times stronger than the light you put in. So you can see cancer cells. So you can use it for detecting cancer, because you just mix the solution and bind this peptide to it, and it binds to the cancer cell. If the cancer cell is there, you find all the gold nanoparticle on the top of the cancer cell. You know this blood has cancer. So you can detect cancer. You can detect one cancer cell. Second one, if you want to kill it, now that you know that you have it, All what you have to do is use a smaller one that actually, instead of scattering light back to you, it absorbs it and get hot. Okay? And the heat goes around and the solution itself starts killing the cancer cell. Okay. Then let me show you here some of the results that you have here. Here is here are different cells. These two cells here are cancer. This cell here is not, it's a healthy cell. And you mix the three of them with the same amount of solution that has this large gold nanorod that scatters light, and with this peptide. You have to put the peptide here that binds it to the cancer cell if there is cancer cell there. So you can see the first two are cancer, and indeed, look at all the scattered light coming back. All of it, all the light coming from the cell itself, the top of the cell itself. And this one here does not have cancer, so the nanorod doesn't bind to it. It's in solution everywhere, but not on the cancer cell itself. So you know this blood does not have cancer. This blood, these two types of bloods here definitely have cancer. Simple experiment under a biology microscope. This is nothing fancy microscope. One of your biology labs have these microscopes. Okay. Now you can also, you can use it. Now this scattering light is very useful because if it binds to the cancer cell, and if the cancer cell is moving, you can see the scattered light is moving. So you can actually detect it to determine how good a drug for cancer is. Because as long as the cancer is the cancer cell is moving, you see the scattered light is moving. But once it dies, you see it standing still. So here is the two things here. Let me just show you here and here. This one is not moving. I don't know what the heck. There we go. You can see cisplatin, and you can take a stopwatch with you and see when does the movement stop, because the first one is already stopped, and that is cisplatin, kills the cancer cell immediately. So it stops the movement. This one took much longer. This kind of drug is not as good. In fact, let us do it again. Let me see if we can get them back again. Okay, let's get. Here we go. I'll put them at the same time. Now watch this. The cisplatin, the cells are moving, but then the drug kills it. It's stopped. So this one is stopped. So you know how long it took that drug, this amount of drug, to kill cancer cell. The other one is still going. That means this drug really is not very efficient. It's not very good for the cancer cell. It can determine how good a drug is killing cancer cells. Okay. We try to make more science out of it. You use Raman spectroscopy, and then you can see vibration bands of the cancer cell during its as it dies, and hopefully you understand the mechanism, the molecular mechanism of how does a cancer cell die when you give it a drug or by itself. So I will just show you some of the results without having. Here is, for example, here. Okay, let's keep going here. There you go. Here's this is the Raman spectrum, and take a certain amount of the cancer cells, and we get from the scatter of it, we can see the different vibrations around in the cancer cell, and with time, as the cell is going through life, or when it dies, there are changes of molecules. So you see vibrations here are characteristic of the molecule that you see, that our scattered light coming out show us, okay, in the cancer cell. And you can see here, for example, we give it a drug. So you can see here the vibration spectrum is changing with time. The cell is alive. But watch from here on. Watch right here. From here on, the spectrum doesn't change. The spectrum here is like this time. This 13 hours after we give it the drug, and all the way. So that means at 10 hours, the amount of drug we gave this cell, it died. It took 10 hours for the amount of drug we gave this cancer cell, it died, it kills it. Now, once you understand also these vibrations of death. These are vibrations of dead cells, whereas these are vibrations of alive cells. You can understand, hopefully, the process of death of a cancer cell. You can assign what the mechanism, what are the molecules involved in that, and so on. Okay. You can also, of course, detect cancer from resonance Raman spectroscopy. We're doing that. Now, we can do this also because we said once the drug kills the cells, the amount of drug you gave to the cells killed it, you can see the spectrum doesn't change anymore. So you can add the same amount of different drugs for a certain patient, blood that has cancer, and you can tell what is the best drug for this patient. Because, you know, as soon as the spectrum stops changing, you measure the time, it took so long, so the drug that took very short time to kill it, and you see the spectrum become constant, that is the good drug for this patient. So you can even get more involved. But for us, of course, as chemists, we like to understand the mechanism of killing itself. So from the different bands that appear in the Raman spectrum by different drugs trying to kill it, you can get an understanding. It opens the whole field of us to try to understand the mechanism of drugs killing cancer cells. وطبعا different drugs, different cancer cells. So this is opening up a whole new field in this area that hopefully will help understanding how does a drug interact with cancer cells. And this itself get us to understand what is the mechanism of death of cancer cells and what's cancer is all about. And hopefully one day we can stop it somehow, hopefully. Now, we, of course, we did quite a bit of work on, then you ask yourself, how about in mice, in animals? Of course, we want to get to do all these things in human, but of course you can do it cells, of course you can do it in human, take blood outside the cell. But if you want to do anything inside a patient, then you got to do as a drug. You want to use a drug to kill cancer inside a patient. Well, that's a medicine. Medicine, it's a long way to get from experiments in the lab and things like this to actually experiment on human. I take a certain drug because I know it kills the cells and I know how it kills it and all these things. But you cannot, for example, how does the photothermal heat kill cancer cells in the body of a human? You cannot use it. You cannot use this method to save a patient unless you prove to of course, the health department that there is no long-term effect. You got rid of cancer, but does it say 5 years later you get a worse disease than cancer, or does something else? And so these are the things now to take it to human. You have to do a lot of experiments. I'm sure you all know about this. And so we had to start understanding how does cancer interact with different animals. I mean, we said we killed cancer, we did it in mice before. And then you have to go to human to see if really it does the same thing or not. Well, that's a little bit more, take a longer time, and we are really in this time now. You have to do it on many animals, and you have to show that does not have other effects. It might kill cancer and produce a worse disease inside the body. So you really have to very much to make sure that it does not have any effects. Yeah. So that's what we started, and in the USA we did the mice. That was easy. You don't have to get permission to do mice. In fact, you don't have permission to do dogs or any animals. You don't have to get permission. But to get it to human, you have to do it to all these animals and show it did not do much bad effects on them. And then you hope that the FDA in America or وزارة الصحة هنا to agree to it or not, and so on. So that is what is taking us now the time, the last several years, to do it on animals and different animals and so on. We were able to do it on mice in the United States. It was a simple proposal and was not expensive, not expensive at all. And we were able to do it on animals with the cancer system there, Cancer Society, and at Emory has a very good cancer center. So we wrote a proposal to NIH that we like to do to see if we can cure the cancer over mice, or many mice actually, and to prove that it is useful for the mice, and there is no after effect that you do that. So you can see here we start doing, but then it worked beautifully on the mice, very nice. Now we tried in the United States to do it on dogs, you know, and we wrote a proposal, and with a very you have to have with you a doctor animal that knows how to handle animals and so on. And she told us it's going to be very expensive and it's going to take a long time. Why? Because here in America, you don't go to a person bringing you his or her dog and asking you to cure its cancer, and you tell them, can we try a new method? They immediately say, give me the dog. Excuse me, I don't want you to touch it. Get away. Cats and dogs in America are like members of the family. It's just like their son and daughter. You cannot take it to try something on them. So she said that it's going to take a long time if you find somebody that will take a chance for science sake and see if it works or not. So the NIH itself, it was so expensive that they couldn't support it. So I gave that kind of seminar in Egypt almost 10 years ago, 7, 8 years ago. And it was written in the paper and things like that. And Masr al-Khair is a very nice organization. Ali Guma, he's the head of that. And they collect zakah, meaning nas, and they use it for important things to help these diseases or poor people and so on. So he read it in the paper, so he told the Egyptian health center there, he told them that if you get Professor al-Said to work with you on this, we'll give you all the money you want. So they contact me, they send me the paper that was mentioned, and I said, sure, I'll be glad to, be no problem. And we have been working with them since then. And then another group, I went to the government, I told them, I will feel much happier if you give support of another research group in another organization at the University of Cairo, actually, the animal department there, and they want to do the same thing. But it would be nice if they do the same thing and they got the same results, as long as they don't talk to each other. They both of them said, we're not going to talk to each other. We're not going to tell them what we're doing. No, that will be okay. So I was able to get money from the government for this other group, and both of them are doing beautiful work. My God, really incredible. I can't. It's interesting. It turned out each group were doing slightly different things. They were trying to cure, of course, medicine, but the university people, of course, are more interested in the mechanism, the molecular mechanism of things. The other group, they just want to cure as many animals as possible and get the statistics and so on, but that's what we need. But the other group at the same time try to understand what are the molecular mechanisms of curing cancer by a certain medicine or something like that. So it turned out they don't know that, but it turned out working independent was extremely useful actually. So these are histology of different, the important thing is you have to prove to the health department there is no long-term effect. You can cure the cancer now, everything is happy, but say 5, 6 years from now, you get another disease we don't even know about, see? So that is what they want to do, long-term results from that. And you can see here, 15-month effect, the different thing here, they show, and then here, 1 month after the treatment, 15 months after the treatment, and you can see similar effects. They said from the people that know the biology of this, they say it looks exactly the same, just getting older, that's all, from here, the kidney here, 15 months, this is 1 month. So they said at least 15 months, there is no 15-month toxicity for this. And they did the photothermal treatment effect. Here is animals that were treated, and this animal were not treated, and you can see the efficacy, the effect of the treatment is certainly quite different. Here is a very interesting, very impressive result. There was a cat that had a huge cancer here, and one of the interesting thing about this is that, I mean, this would never surgery. You cannot cut all of this. This is huge, half of her body, 1/3 of her body. It's just, it would have killed the cat immediately, of course. But thank God, after few treatment, they had to do it several treatment, 4 or 5 treatment, and after that, everything went down. And more important, that there were some questions that after special breast cancer, whether the ladies get children or not, get pregnant or not. And so that was an interesting experiment they did, and they cured this, and indeed, after a few months, she got pregnant and got 3 kittens, and you can see they all happy. They've been now about 1.5 years, and the cat is nothing came back. That's very, very important. Does it come back or not? Was a very important thing. And after 1.5 months, this cat certainly did not come back down. But now you have to take long time toxicity measurement, because FDA will not accept a few months even. They want to take long time toxicity, and that's what they're doing quite a bit in Egypt. As I told you, I don't do this in the States anymore. I come to Cairo, and these 2 groups are working, and they don't talk to each other. They talk to me, thank God. I know everything they do, and they are really working very, very hard on that. And these are different results. You can see the treatment, the effect of the treatment. They actually discovered very new, interesting method. They found that actually surgery is one of the things that gets the cancer back, actually. And so they were able to compare 2 types of treatment: the old method, doing surgery, cutting the cancer out, and the other one by photothermal, just heat it and slowly seeing it disappear. And they found out that if they do surgery, straight cutting and so on and so forth, it appears very soon after that. Few months after that, because cancer appears somewhere else and so on. By this method, photothermal method, cancer never appears again. And that is itself is telling us something about cancer, which we're trying to understand right now. Here is a very interesting thing here. Let me show it to you. Yeah, they treated different methods, and they see that indeed the photothermal, because it doesn't open, it doesn't cut, it doesn't do anything, it doesn't spread anywhere else, and so on. And they did now toxicity for several months, and they measure chemical. زي ما حضرتك بتروح, when you go to the doctor for a checkup once a year, all these examinations that the doctor give you, they did it every several months after the treatment. And they saw chemistry did not change. That means there is no effect of the treatment on the body medicine or body chemistry. You see, it's very, very important. So these are different chemicals, and as a function of time and all these things, and they have the methodology to measure everything and things like this. There was no, and they have to do this to take it to Dr. Saha to show them what the results that are there, and everything is okay. Here's a very interesting case. Here's they even discovering new methods of treatment of surgery. Here is they found that if you take this dog here had a huge one here that spreading, and it was so big that to treat it by this method will take a long time because you have to do it and go down a little bit, and some more injection and light and goes down a little bit. It will take a long time. So what they did surgery first. They completely cut the lump out, throw it out, and then they photothermally sprayed the gold nanorods on the whole area there, and they exposed it to light, and that's completely cured it. More important, it did not come back. If you do surgery, a lot of the time the thing comes back. This we're trying to understand on a molecular level too, but will be very, very interesting. Yeah, in fact, you can see here they treated this part here by photothermal. They treated this by surgery, and indeed, after a little bit, it came back, started coming back and opens up the skin and everything. But if they do it and shine light on it with the golden particle afterwards, they found that indeed it does not come back. It does not come back. So it's a new method of treatment. Yeah. So this is some of the summary and conclusions. There is no evidence long-term toxicity of gold nanorod in mice model, and the gold nanorod, this method, is effective in treating natural memory, gland, tumors, and all these names those guys use. And 13 months has been treated and the cure and no signs of return. More important, I think, I don't think it returns somewhere else in the body. If they do regular surgery, they found out that after a year or so, it starts appearing somewhere else. Cancer, that's normal. It appears somewhere, and that's what killed people. The secondary cancers that killed people, really. Photothermal method, they found it does not come again in any form, in anywhere in the body. So that itself is the thing that indeed is going to be quite important for that. Okay, those are the people that did the work, the graduate students on the cells and smaller things. And these are the great people in Egypt in different groups that they do the different things. With this, I'd like to thank you very much. Thank you.
Thank you very much, Professor Mustafa. Now it's time for questions. So let's start from Mel. Okay, go ahead.
Thank you, Dr. Mustafa, for the nice talk. Just a curiosity question regarding the gold rods. Would that because of the surface area you choose it, then gold nanoparticles or any other shape for these materials, or just on that?
Thank you very much. Very good question. I'm sorry I missed that. You want to get light that goes into the body. Near infrared light is the light that you use. Near infrared light, you need to absorb it, to heat. The shape of the nanoparticle has to be in a rod shape. Sphere will not absorb near infrared light. And we use near infrared light to go inside the body to where the cancer is. Right. Very good question. Thank you very much.
Thank you. Any more questions here? Yeah, go ahead.
Thank you so much, Prof. I have two questions, please. The first one, you injected these particles as an uncoated or coated particles first. The second question, what is the beyond mechanism of loving the gold nanoparticles to the cancer cells over the normal cells? Thank you.
What happens afterwards?
Again?
The second question, why these gold nanoparticles love the cancer cells? Because you said that these particles go to the surface of cancer over the normal cells.
Yeah, it doesn't. The gold nanoparticle itself will not go and hook to cancer cells by itself or anything. What we depend on is that once you heat the nanorod in the media where cancer cells are, this media become hot. And then the cancer cell in the same medium, the heat itself will kill the cancer cell. In the beginning, we thought we had to bind it to the cancer cell itself in the beginning. And that's why we got all these, long chain things. But then we found out it doesn't make any difference. You can just as long as you heat the region itself, that's enough. Good question. Thank you.
A female section, any question?
Yeah.
Yeah. Okay.
Thank you. Thank you. Thank you, Professor Mustafa, for your interesting presentation. I'm Yani Rizjani from Brawijaya University, Indonesia. I would like to ask you a question about drug efficacy for cancer cells using a dark field microscope. Did you use a certain staining method for bioimage of cancer cell? For example, did you use antibody or something, other material labeling methods for dark field microscope using living cell bioimaging to present a fluorescence image? Thank you.
I'm sorry.
أنا وش استخدمتها عشان you use to make like images in
Oh.
the microscope.
Oh, I see. Well, actually, we just looked. I mean, I mean, what we did, I had my son was a cancer doctor himself, and all what we had to do was just to mix the solution, and then he took just one drop and put it on a شريحة, this glass thing for the microscopes, and just looked in the microscope itself directly. Yeah, and just make an image of that. You can take a picture of that. Also, in the microscope itself can give you a picture of that if you want it. Yeah.
Thank you.
This is what. Yeah.
I guess so.
Okay. Very good. Thank you.
Any more question from your side, female?
Yes. Yes.
Okay, good.
Please.
Thank you, Dr. Mustafa, for your lecture today. I want to ask about the gold nanoparticles. Has it confirmed to be a way of treatment of cancer on a human? And is there any side effects of that method? Thank you.
Yeah, human, we did not get to. That's why we hope to, by doing all these animal experiments and going from one animal to the other. We actually cured the cancer on the back of a horse the other day. The more animals you do, the more animals we do, the more proof and make it easier for Wizard al-Sahra approve it, you see. That's what and we have to have with us medical doctors and cancer medical doctors themselves with us, actually in these experiments, always with us, cancer doctors, and they are the ones to write to the Ministry of Health what have they seen and what is it good or bad or whatever. And the cancer doctors in Egypt are the ones that definitely have to write the final reports of what they have seen, and because they do not take our word, because they have somebody that understands cancer itself. Yeah. Thank you.
Any question from them? Okay, go ahead.
Yes.
No, just a second from here.
Thanks a lot for your presentation, Dr. Mustafa, and we acknowledge your effort to treat cancer. And we have the cat and the kitten. We acknowledge your effort to treat this cat. And I'd like to ask about what is the metabolism of gold nanoparticle. It's easy to extract from the body of human cell.
Very good question. Where does it go? Where does gold nanoparticle? It does not come out. That is for sure. But we had some pictures of the spleen and the liver. They are the cleaning organs. Everything goes through there to clean up. And indeed, it goes there. I'm sorry I did not have this thing, but the liver is huge, and this few nanoparticles that did this thing is a very, very small amount, and it doesn't really change very much. Over 15 months period, it gone down a little bit in the amounts, but not that much. But more important, it did not do any damage to the liver itself. The size of the liver never changed, the size of the spleen never changed. But that's very, very important, of course. And that's what they look at. And the longer, we want to do it longer and longer, so it shows that these organs does not get changed over the period of time, over lifetime remaining of the patient probably, yeah. But that's very important, yeah, thank you.
Any more question from this side? Yeah, go ahead. Sir.
Thank you, Professor Mustafa. Did you study the activity of nanoparticles with elements other than gold?
Over?
Other than gold, other elements.
Yeah, we are studying this with animals, yeah. All these experiments that we are doing now, animals are the ones that we deal with. We don't, I mean, did I get your question right?
Offer other metals.
Very good question. Yeah, sorry. Silver is no good, unfortunately, but it is good for other things. I mean, if you want to kill something, it will kill it, and so they use silver to kill certain insects or certain things that you don't want. And we found that also is not good for normal cells that we have. Yeah, it gets some kind of oxides. I think this silver oxide and all kinds of chemistry takes over, much more active. Gold nanoparticles somehow is not active in the body. Yeah. Good question. Thank you.
Female section. Any questions?
Yes.
Mm-hmm. Go ahead.
Thank you, Prof, for this amazing lecture. But I want to ask, how did you prepare the drug or synthesize it? You already talked about the technique, about how the drug interact with the cancer cells. But how did you prepare this drug?
How did I pick up?
No, prepare the drugs.
How you make the gold nanoparticles?
Yes.
Yeah, sure. That is really fairly easy. Essentially, you reduce gold salts, essentially, but a certain way, and not very fancy way. But then you have in the solution a chemical that binds to the surface of the gold nanoparticle, and by adjusting the concentration of this chemical to the concentration of the gold amount itself, and as the gold nanoparticle grows, it starts getting bind around it, this binding organic compound, and once you have adjusted concentration right, it can get enough of it that no more gold can be deposited on the one that you already have. So it stops growing. So just adjusting the concentration of the thing on the bind that put on the outside surface with respect to the gold ion itself. And that will give you the size you want. The smaller amount of this solution that binds on the outside, the larger the gold nanoparticle becomes, right? Good question. Thank you.
Thank you. Yeah, okay. We'll take the last question.
Sorry, but I have another question.
Okay.
No, just a second. Question from our side.
Okay. Thank you very much, our respected Professor Said. I just have one question about selectivity of gold nano root for treatment of different tumor cells. There are many tumors, like, for example, stomach, colon, or brain. If there are any selectivity for gold nanoroot for that? Thank you very much.
You mean do they bind specifically to something or the other?
Yeah.
Yeah. Well, no, it really we just try to if you specifically want to bind them to the cell, to the cancer cell, you bind this molecule I showed you in one of the slides, the early slides. And this molecule binds on one side to the gold nanoparticle, and on the other side, it has a functional group that binds to the surface coverage of the cell itself. But we found that we really didn't even need that. We don't need that. If you have enough of each one of them, you have the heat itself will do it. Yeah.
Okay. We said the last question from the male section, but The female will still have one more. Okay, go ahead. Any?
Prof, you said that silver has some toxicity, so it will be not useful for this treatment.
I'm sorry.
Silver is toxic. Silver is toxic. مضر سام السلفر.
The gold or the silver?
Silver.
Pardon me?
The silver.
Oh, the silver, yes. Silver, yeah, silver is we found that it does kill the cells. It does kill the cells. And that's why we stopped it. But of course, if you want to kill bacteria or something, silver is wonderful. And I used it for years actually. And but for some reason, it just we found that it kills the cells that we have, and we stopped using them immediately. Yeah.
Either as a nanoparticle.
Pardon me? I'm sorry.
Even if it's
Either as silver nanoparticles also.
Any other?
even if it's nanoparticles, the silver nanoparticles.
Silver nanoparticle, yeah.
It is.
Silver nanoparticle, the nanoparticle itself also does damage. Yes, right.
Thank you very much, Professor Mustafa. Thank you very much for your attention.
Thank you.
Now, Professor Hamad Al-Khatlan, the chairman of the scientific programs, want to announce something. So, welcome, Professor.
Assalamu alaikum wa rahmatullah. Good morning to you all, and again we would like to welcome you to this conference, and we hope you will enjoy your stay with us at King Saud University and in Saudi Arabia. Just two short notes about the scientific program. The scientific program you have with you are 3 sessions in three different conference rooms. We got news this morning that some of our colleagues are late to arrive with us, and we have to reschedule their talks. So all sessions, 3 sessions, will be in this conference room. So after our break now, we will come back all to this conference room. We will have all 3 sessions together until we reschedule the other guests' lectures. The second announcement is about poster presentations. The list of poster presentations, we have 522 posters accepted, and the list of the spreading over the 3 days of the conference is available on the website. But if any of our guests did not log into the website and see what is the time for his poster presentation, we will have this list available on the registration desk, inshallah, right after Salat and lunch break. Thank you very much.
I ask the speakers of this morning to be present here, please, before they go to break. All the speakers of this morning, all the sessions, to come here before the break, please.
السلام عليكم. صوتنا راجع. السلام عليكم. باشمهندس صوتنا راجع يا جماعة. Our sound is returned. ما هو السلام عليكم. السلام عليكم. هو أنا ليه ولا متوطي قوي؟ السلام عليكم. باشمهندس لو سمحت صوتنا راجع خالص. مستر بن. عايزين نجرب ساوند كومبليت دلوقتي. خلاص زي ما احنا. زي ما احنا كده اهو. هنعمل
How the system is
Test one.
voice.
Test.
السلام عليكم.
عليكم السلام.
Our sound is okay now. Is okay now. Good. ما فيش صورة دي. طيب بصري. اوكي يا حبيبتي. اتفضلي. ايوه.
السلام عليكم. السلام عليكم. السلام عليكم.